Hello, today we're going to start looking at CHATELIER'S principle. So it's important to remember that your equilibrium expressions, you always write the products over the reactants. You only include aqueous or gaseous substances. And K, the equilibrium constant, is temperature dependent. So typically in a lot of questions you'll see like at 25 degrees Celsius, the value of K is some number. That's because it will be a different value at different temperatures. So that's kind of just important to notice because in this section we're going to start changing the temperature. So you need to be aware that when the temperature changes, the value for K will change. Okay, so a guy named Le Chatelier came up with this principle, and it has to do with reversible reactions, so chemical equilibrium, reactants, and products. So he figured out that when there is some kind of stress on a chemical equilibrium, the reaction will either proceed in the forward or in the reverse direction in order to relieve the stress. So kind of think about it this way. The first step, it's at equilibrium. And then the second thing, there's some kind of stressor. And then the third thing, and the thing that Le Chatelier's principle is kind of focused on, is how are we going to relieve the stress to regain equilibrium. So a lot of people think that when you're using like an ice chart, you're starting from initial conditions and reaching equilibrium, that's Le Chatelier's principle, and it's not. Le Chatelier's principle is when you're starting at equilibrium, changing something, and then how do we get back to equilibrium. So just be really careful when you're dealing with that. So the first thing we're going to talk about, the first kind of stress we're going to talk about with Le Chatelier's principle is concentration. So let's say we have our reactants and we have our products. And let's say, for example, that they're both aqueous. Okay. If I suddenly increase the concentration of my reactants, increase the molarity, you could do this just by dumping some more in, or by adding some kind of reactant that will dissolve to produce that reactant. But in whatever case, you're increasing the concentration of a reactant. It means you have too much on the reactant side now. That's your stress, too much on the reactant side. In order for us to relieve that stress, it's going to proceed in the forward direction, or we'll say it will shift toward the products. Now let's say, for example, we have an equilibrium system again. Still aqueous. If I increase the molarity of my products, well, now I have too much on the product side. That's my stress. I need to use up those extra products, so it will shift towards the reactant side. You can also decrease the concentration as a stress, so that we have our reactants and our products. If I were to decrease the molarity of the reactants, maybe I add in something that removes it from the solution, that binds it up. So if I decrease the molarity of the reactants, now I don't have enough reactants. That's my stress. I don't have enough. So I need to make some more. And so it will shift in the reverse direction, and it will shift towards the reactants. Try to avoid saying left and right. Just a lot of times people can mix those up or just get them confused. So if you get in the habit of saying shifts towards the reactants, shifts towards the products, that will be more accurate in every situation. And then our final example, if we have our reactants and products, if I were to decrease the molarity of the products, again, you can do this by adding something that binds it up, or if you are like physically taking it out, now you don't have enough products, that's our stress, so we need to make more products by shifting towards the product side. And so that's how concentration affects it. Now, I used aqueous things as an example, but they could also be gaseous things. You can calculate the molarity for a gas, just like for aqueous solutions, by doing the moles per liter. So, yes. Remember, when you're adding or removing liquids or solids, as long as you still have some available for the reaction to happen, changing the amount of liquids and solids will not shift the reaction equilibrium. Okay, so our second stressor has to do specifically with gases. And this one I'm going to use kind of a fake reaction here. Let's say I have A plus B yields AB, and let's say they're all gases. Okay, so when you're dealing with pressure or volume of gases, you need to look at how many moles of gas there are and on which side. So moles of gas is the important thing. So in my fake reaction here, I have 2 moles of gas on the reactant side and only 1 mole of gas on the product side using their coefficients. All right. So you just need to count up the moles of gas on both sides. And if solid, liquid, aqueous, you ignore it when you're dealing with a change in pressure. So if I were to increase the pressure on a system, the most frequent way that this happens is by decreasing the volume on the solution or on the system. When you increase the pressure, it will shift the reaction toward the side, whichever side has less moles of gas. So if you think about it, the stress is that there's too much pressure. That's our problem. We need to solve the problem. And if there's fewer moles of gas, that means there's going to be less pressure, according to Pivner, right? So if I decrease the pressure, it will decrease the moles. If I have fewer moles, lower pressure. We'll fix that problem. Now, the opposite, if I were to decrease the pressure on the system, typically by increasing the volume, it will shift toward the side that has more moles of gas. And again, according to Pivner, so if I have too little pressure now, I need to increase the pressure to get back to equilibrium, so I need to get to the side with more moles of gas. So in this fake example, if I were to increase the pressure, it will go in the forward direction. It will shift towards the product side because there's fewer moles of gas. And in this fake example, if I were to decrease the pressure, it's going to shift towards the reactants because there's more moles of gas. Okay, so now we need to talk about temperature. Temperature depends on whether the reaction is endothermic or exothermic. So let's go ahead and make 2 examples here, reactants to products, and I'm going to put heat. So this is an exothermic reaction. Heat is on the product side being released. And we have an endothermic reaction, reactants, products, so heat will be on the reactant side. Remember, exothermic delta H is negative, and endothermic delta H is positive. Okay. I always like to write the heat in as a reactant or product because it helps you to figure out which way it's going to shift. So if you were to increase the temperature, increasing the temperature, it will be too hot, so it's going to shift away from the heat. And that's true for both types of reactions. Shift away, I can't write today, away from the heat. But if I were to increase the temperature, it will shift toward the heat. So the way that I like to think about it, decrease the temperature, there we go. If I increase the temperature, I think it's too hot and I want to get away from the heat. So in an exothermic reaction, that means it'll shift towards the reactant side. But in an endothermic reaction, it will shift towards the product side because it goes away from the heat. Now in my second type of stress, if I decrease the temperature, that means it's too cold, we need to go toward the heat. So in an exothermic, it will go towards the products, but in an endothermic, it will go towards the reactants. Now, remember I said that this will affect the value of K, okay? So once you figure out which direction it is shifting, then you need to look at how the value of K will change. K is products over reactants. So let's say I have an exothermic reaction and the temperature increases. So it's going to go towards the reactant side. Well, I have more reactants now, and that means it will decrease the value of K because the reactants are on the denominator. But if I take that same exothermic reaction and I decrease the temperature, it's going to go toward the heat, towards the product side. I'll have more products, so I will have a larger value of K. In all of the other types of stress, so concentration, pressure, or volume changes, it will always reestablish so the value of K stays the same. But if the temperature changes, K will also change. It might not change a proportional amount depending on the stoichiometry of your reaction, but you can predict whether K will increase or decrease by looking at which direction it will shift. So just be careful there, okay? So let's talk about catalysts for a second. So we remember from kinetics that catalysts will change the energy of the reaction by lowering the activation energy. So if that is your normal energy profile, using a catalyst will make it lower activation energy, but it will not change the starting or ending energy levels. It will also not change the net change in energy, or delta H. Okay, delta H stays the same. It's just the activation energy that changes. Now, we're talking about reversible reactions now. That means you're going to be able to go in the forward direction and in the reverse direction. The good thing about catalysts is because it lowers the activation energy in the forward reaction is right there without a catalyst and here with a catalyst. The activation energy in the reverse direction, if you're going this way, the activation energy for that uncatalyzed is there, and for the catalyzed is there. So no matter what, if you use a catalyst, it will increase the rate of both the forward and the reverse reaction. And because of that, catalysts do not have an effect on your value of K or on your position of K. So that means sometimes they'll try to trick you with questions where they'll ask you about how a catalyst will shift the reaction towards the product or the reactants according to the CHATELIER'S principle. It doesn't do that at all. It will reach equilibrium faster because it's lowering the activation energy, but the equilibrium position does not change, and the value of the equilibrium constant does not change. Okay, so we have this reaction. The COCl2 decomposes into carbon monoxide and chlorine gas, and they gave us the value of KEQ is 0.0071. We're going to predict how the reaction will respond to each of the following stressors. If I add more COCl2, increasing the concentration, I need to use up that excess, so it will shift towards the product side. So I'm going to write P for products. It's going to shift towards the products. Now for B, let's say we're removing CO, taking some of that out. Maybe it's escaping somehow. I don't know. They're removing it. That's my stress. I have too little products now, so I need to shift it towards the product side to make more of that CO. So it shifts towards the product side. Now if I increase the pressure. For pressure, I need to count the moles of reactants and products gases. So I have 1 mole of gas versus 2 moles of gas. Increasing the pressure always goes to the side with less moles of gas. So it will go towards the reactant side. And then decreasing the temperature. So right at the very beginning, they told us it was endothermic. So heat is on the reactant side. If I decrease the temperature, it's too cold. I want to go toward the heat to warm it back up. So it will also go towards the reactant side. Our last example, we have this reaction, which is the Haber process. Nitrogen and hydrogen react to form ammonia. It says it's determined that increasing the temperature causes the equilibrium to shift towards the products. Does this mean the reaction is endothermic or exothermic? And explain. So increasing temperature, it will always shift away from the heat. So in this case, it shifts it towards the products. So that must mean it's away from the heat. So the heat must be on the reactant side. So that means that it is an endothermic reaction. In this case, I would kind of use a claim evidence reasoning format for this type of free response question. So my claim is that it's endothermic. My evidence is that when you increase the temperature, that means it has to go away from the heat, and away from the heat is towards the products in this case. And so then my reasoning is that the heat must be on the reactant side. If shifting towards the products means it's going away from the heat. Also, when you're doing these types of Le Chatelier questions, it's always a good idea to, in your reasoning portion, include Le Chatelier's name. There's only two guys that I would really recommend knowing their names for AP Chemistry, and that is Coulomb, of course, and Le Chatelier. So you would say something like, according to Le Chatelier's principle, as you increase the temperature, you shift away from the heat, or from the opposite side of the heat, so the heat must be on the reactant side. Something like that. So I like to say name drop Coulomb and Le Chatelier. Now in part B, if the reaction is at equilibrium and the pressure is increased, in what direction will the equilibrium shift? Well, my reactants have 4 moles of gas, and my products have just 2 moles of gas. If the pressure is increased, I need to go to the side with less moles, so it will shift towards the products.